So, welcome everyone. Thanks so much for joining us at our monthly AI meetup. My name is Sheikh Jubair, and I'm a machine learning scientist here at Amii at the Advanced Tech team. Before we get started, I just have a few notes. We'd love to see your faces. So if you're comfortable, I would like to encourage you to turn your cameras on. We're recording this session so that others can check it out later on. It will be live in our website and at the Amii YouTube channel. If you haven't had a chance to check out our other recordings, we highly recommend to do so. There's really some great videos out there. We have an amazing speaker today, Marlos Machado. He is an Amii Fellow and Canada CIFAR AI Chair. Please either write your questions in the chat box below or feel free to raise your hands and ask your questions throughout the presentation. Finally, our next meetup is scheduled for Tuesday, July 19th. So make sure you follow us on social media and sign up for our newsletter to keep up to date. Now let's get started. Marlos Machado is a senior research scientist at DeepMind, Alberta, an adjunct professor at the University of Alberta, and an Alberta Machine Intelligence Institute fellow, where he also holds a Canada CIFAR AI Chair. He received his BSc and MSc from UFMG in Brazil and his PhD from the University of Alberta. He was a research scientist at Google Brain from 2019 to 2021. Marlos' work has been published in the leading conferences and journals in AI, including Nature, JMLR, NeurIFS, and ICML. His research has also been featured in popular media such as BBC, Bloomberg TV, The Verge, and Wired. I'll hand it over to Marlos now to share his screen and get started. Take it away, Marlos.
Thank you, Jubair. Let me share the screen. So can people see my screen? And if yes, can you say yes? Because I'm just seeing my slides. I'm not seeing people nodding.
Yes.
Perfect. Thank you very much. So I'm going to start now then talking about this work about autonomous navigation of stratospheric balloons using reinforcement learning. As I said, I'm not seeing your faces. I really wanted to, but I have to share my whole screen and then I have to be seeing my slides, meaning that you should just feel free to interrupt me, shout, or anything if you have a question. You can also type the questions on the chat, and then Jubair will keep track of them. So this talk is about some work that I did when I was at Google Brain, and it was in partnership with Mark Belmar, Pablo Castro, and Ziyu Wang, who are also from Google Brain, but it was also a collaboration with Loon. So Sal Candido, Jun Gong, and Sam Ponda were researchers or engineers at Google at Loon, and I wanted to share this work with you today because it is the story of a deployment of a reinforcement learning agent into the real world. But I think that more than that, it's about some of the lessons learned and some of the things that we did and how we model the problem in a way that hopefully it goes beyond just this use case, but you can actually see the potential and the impact of these ideas across all sorts of other problems that we might have. I don't think I have enough slides, meaning that really, if you have questions or you want to make a discussion, you can do that, and I will make sure that I control the time. The short version of this talk, the very short version of this talk, is that in December of 2020, we had this paper accepted at Nature, which is the most prestigious academic venue in the world, where we were reporting that we are actually deploying reinforcement learning algorithms in the real world, where we were navigating balloons in the stratosphere. And this talk is the story of how we got there and what are the things that we did. The roadmap for today is that I'm going to spend some time talking about the problem that we're trying to tackle. Then I'm going to talk about the solution. And then I'm going to discuss results in both simulation and the deployment in the real world. And I'm going to wrap up with some thoughts on the general big picture of this. My goal with this talk is to make it fairly high level. So I'm not going to delve into details of the solution or anything like that, but to focus on what I think is the most relevant message in terms of applying machine learning in the real world, and more specifically reinforcement learning. So let me start with the problem. What is the problem that we wanted to solve? So this was a problem that, so this is a slide that Loon has, and I think that it explains their approach to what they were trying to do fairly well. The idea that Loon as a company had was to say that they wanted to provide internet to people who didn't really have access to internet. The way most of us get internet is with cell towers. And a cell tower in the city, that has this coverage of, let's say, 6 kilometers, meaning that if you put a cell tower downtown in Edmonton or in any neighborhood of Edmonton, you're actually serving internet to a lot of people, right? Because that's a pretty big area. The problem, though, is that there's a lot of areas in the world that are very sparsely populated. You can imagine some rural region, the Amazon forest, for example. Imagine that you want to serve internet in the Amazon forest. There's going to be tribes scattered around the forest, but each one of those tribes are going to have maybe dozens of people. So one, it's kind of hard to justify the cost of building a tower to serve a handful of people. And it's even hard to get there to build a tower, right? But if we could build this tower, then we would need a really high tower. If we had a tower that it's 20 kilometers long, let's say, a cell tower, then we would have a much bigger coverage, and then maybe it would justify the cost of building that tower. Of course, we don't know how to build towers that are 20 kilometers long, and that's where Loon comes into play. Loon's had this idea like, what if we flew balloons in the stratosphere? And these balloons are the things that actually provide internet to people. So they're not actually a tower, but they operate as one, right? And their goal here is that they're going to fly balloons in this 15 to 20 kilometer height, which is actually much higher than airplanes fly, or that the atmospheric phenomena that we observe happen. And this was the idea. The catch, though, is that balloons don't just stand still, right? Balloons, the balloons, they stay where they are, and then once a wind blows, the wind will blow the balloon to a different location. And these balloons, they are not propelled, meaning that the balloons really rely on the wind to be still. It only happens that it's quite rare that there are no winds, so the balloon is always being blown to one side to the other. And the problem that we wanted to solve is this problem of what we call station seeking, which is we're going to try to navigate this balloon, riding the winds, sailing the winds in such a way that they mostly stay at the location that we wanted to serve. The way this happens is that you can think about it as like, if we're high up in the atmosphere, there are going to be winds at different altitudes. Winds are blowing at different directions, at different speeds. And because these balloons are not propelled, all they can do is to go up or go down. And I'm going to show the balloon and explain how this actually works. So basically what the balloon can do is this is what this very cartoonish diagram is trying to show. What the balloon can do is to go up to try to find a wind that is taking it where the direction it wants to go. And then if the balloon is leaving this direction, maybe the balloon can go up or down again to try to find a different wind current that will again take the balloon, and then that's basically the goal. So in this example, for example, the balloon that is going up, we can think about maybe the balloon wants to serve this region of mountains. And by doing this loop that it just did, it was serving this region of mountains longer. Okay. So that is the problem. That's the goal that was motivating Loon, and that was the problem that we're tackling in the stack of things that Loon had to do, which is how to better navigate these balloons. And let me give you an overview of this balloon, because this is, one, it's interesting, I find it interesting, and two, because it's going to be relevant for later in the talk. So the balloon, one, it's fairly big. It's like, once it's fully inflated up in the stratosphere, it's 15 meters long, meaning that it's like the size of a tennis court, right? The balloon, it's a fixed volume balloon. What this means is that once the balloon is up in the sky, the envelope doesn't change the volume. So the way the balloon operates is that if you want to go up, basically if you have a fixed volume, All you have to do is to make sure that you're less dense than the air, meaning that, well, you can open a valve, air is going to be pumped out, not pumped out, like air is going to just go away. There is no pump when you open the valve, and basically the balloon is going to have the density of the balloon is going to be reduced, and then the balloon will rise, right? Alternatively, if you want the balloon to go down, basically what you do is that you pump air into the balloon. So now you have more air for the same volume, the balloon is more dense, so the balloon sinks. This is exactly the same thing that happens with submarines, for example, but this is happening in the air. And one thing that is particularly important here is this payload and let me sure that it's this payload here. It's where all the communications are happening and so on. And the important thing here is that we have solar panels. So this balloon is solar powered, and so we have to rely on the sun to get power. Okay. I generally, when I'm giving talks, I like to have this pretty images of the agents running. It's kind of easy to give talks when you're doing research with robotics, for example, because you have these robots and then you show them around, and people like to see those things. Unfortunately, we cannot do these things for the Loon balloons because they're flying really high in the stratosphere. That being said, it used to be the case that if you went to one of those websites that you could actually track flights, you could actually track the balloons as well. You would see a dot and I think this is a balloon. You would click and you would actually see the balloon, its name, and so on. So people did this, or used to do this, and then they would take pictures of the balloons that were flying up above. And these are some of the pictures to just show that these balloons actually exist. But just to go back, and I'm going to use this diagram a couple of times, the problem that we were trying to solve, that we solved when we were doing this work, was this problem of station seeking. And the problem is, again, we want to, there is a region here we would like to serve internet. And then we want the balloon to be inside this region, being able to serve internet. The balloon, it has to navigate the winds, and here what we're showing is that as the balloon goes up or down, it's going to be sailing across the different directions that the wind is blowing. And of course, this image on the left here, it's fairly cartoonish because we're actually talking about 3D problems, right? Like, so it's not only that the balloon is going to go up or down like on a plane as I'm showing here, but then once you go to look at where the balloon actually is, you have a wind field, and this actually varies. This problem is actually quite complex we spent quite some time even trying to think about how we could depict this winds and all the variations that we would have, because it's a fairly hard problem. Every time that the balloon changes altitude, the balloon ends up in a different plane that has a different pattern of winds, right? But that's the problem. And the reason the problem is relevant, and the reason I wanted to talk with you today, is because I think that this problem has a lot of properties that are properties of a bunch of other problems that we have. For example, if you think about this, one of the problems that we have is that we have very complex stochastic dynamics. As I was saying, like thinking about these winds, it's quite high dimensional, it's quite complex. It's hard to keep track of those things. It's not only that, it's so complex that we as human beings, we don't know how to forecast the winds. Like there are papers showing that sometimes we would get an error in our forecast that it's 90 degrees or even more than that. So now think about it, like we're talking about, okay, I'm going to navigate the winds, and I think that the wind above me is blowing that direction, but then you go there and it's actually blowing 90 degrees different than what you thought. Like you're going to in a completely opposite direction, right? Like so. This is already a quite hard problem because we do not even know how to model this part of the world, which again, it's related to a lot of the other problems that we have that we are not able to fully model it, right? There is a question of partial observability as well, meaning that we don't know what the winds look like outside where we are. Given where the balloon is in a given altitude, the balloon knows for sure, like, oh, yeah, I can, in a sense, quote unquote, feel the wind, and I know that the wind is blowing this direction. But the balloon doesn't necessarily know what the wind looks like 1 kilometer above it, right? Because like the balloon doesn't have those sensors, and the forecasts are often wrong. We have
one quick question here, Marlos. Sorry to interrupt you in the middle. So one question came up is, what are the average wind speeds at that height range?
I don't know actually. I know that it varies quite a lot, but I don't have the I don't actually recall the numbers that we would observe. Sorry for
Probably,
that.
uh, what's the effect of the wind speed on the balloon?
Sorry, can you say
Is
that
it
again?
what's the effect of the wind speed? So if the wind speed is very high, what's going to happen with the balloons,
Well,
and
so
what if they?
yeah, so if the wind is quite fast, it's just going to blow to push the balloon faster to a specific region, right? So I'm going to show you this later in the talk, but one way to think about it is like, well, arguably, if you're outside the region and you find a fast wind that it's blowing you towards the region, you should just sail that wind because it makes sure that the balloon is going to arrive there faster, right? Um, but then maybe when you are within the region, you don't want those fast winds because they push the balloon quite fast away, and then you don't want that, right? Uh, is there any other question?
Not at the moment.
Okay, cool. So one more thing that it's important to talk about in terms of problems that like we have this binary signal, you're either inside the region or not, but it's a long-term objective, right? Like it's not that every decision that we make is just going to impact what happens next minute. Like sometimes by making a decision, you know what, I want to go to the top of the altitude that I'm allowed to, like the 20 kilometers. You will go there and you will find, for example, a very fast wind that's blowing you away from where you want to be. And then by doing that, what might actually happen is that you are blown away by 100 kilometers away from where you would like to be. Meaning that this has a consequence, a long-term impact on your objective for like several hours, if not days. So you have to balance those things of like, what is the long-term impact of my actions? It's not only that, we also had power constraints, as I was telling you about. We had solar panels, and we had a limited amount of power that we should consider. So this is actually a multi-objective problem, optimization problem, because it's not only about being within the region, but being within the region while being mindful of the power you're using and things like that. So all this to say that it's just like, I think that maybe people can relate that a lot of the problems that we have, they are problems that have similar properties. This multi-objective aspect, this notion of partial observability, not being able to actually model the world, and decisions that have a very long-term consequence. So I think that this is why this was one of the reasons this is so interesting, is because we were actually using machine learning successfully to deal with a lot of these challenges. One last piece about the problem is that we have the Loon had a simulator. So, but the simulator is kind of different than the simulator that reinforcement learning researchers are used to. Because what happens is that we don't know how to model the winds. I was just telling you this, right? Like, so how can we have a simulator? So the way we did this was that there is historical data about the winds. They are fairly coarse. It's not at the right granularity as we would like, but we had historical data about the winds. So basically what we could do is, in a sense, go back in time and pretend that the balloon is in January of 2013, and then think about, okay, if I were to be in Peru at this altitude, this longitude, this latitude, at this time of the day, what would the winds look like? And because we had a very good model of the dynamics of the balloon, then we could run this rollout, right? Like, oh, if I were here, then if I was to go up, then I would go to this other place. But as I said, the winds were fairly coarse, meaning that we also had to do some interpolation and some statistically plausible way to say that, oh, I know that the wind would be, I'm just making this up, but let's say at 15 kilometers and 16 kilometers. So what would be inside this 1 kilometer range that we don't have the information? We had a better granularity than that. But once we had this, then we had the simulator, right? And then we could actually think about what would happen if we were here and so on. And we heavily used the simulator as we were designing our algorithms and iterating over them. So now I'm going to move to the solution side of things and moving away from the problem. So it's probably a good time to ask if there are any other questions. No?
Sorry, just one question.
Yeah, sure.
So you have multiple objectives, but do you have any constraints, maybe safety constraints?
We do. That's a great question. We do have a lot of safety constraints. The main goal, the main objective, let's say, is to make sure that these balloons were safe, right? We didn't code them up as objectives in our machine learning problem. We had wrappers, if you will, around that would guarantee that we wouldn't do anything stupid, right? Let's say, oh, I want to keep going up, 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 up until the balloon pops. No, there is a maximum altitude we're allowed to go. Otherwise, basically, there is an external process that just overrides whatever. So like, no, don't do this, to make sure that we were within the safety constraints of the problem. But yeah, we did have a lot of safety constraints as well. So
I have a question, by the way, Marlos. So
yeah, sure.
the simulator that's there, so how realistic it is, or how realistically it mimics the real world?
You mean the simulator?
Yeah, exactly.
Well, the simulator was fairly accurate in terms of the dynamics of the balloon. And we have historical data from the winds, meaning that, well, it was something that actually happened, right? We cannot forecast the winds, but we know what actually happened and was measured. So it was fairly accurate. And this interpolation model that would give us the winds at the higher granularity than we would expect, it was actually fairly good. So, I mean, I cannot say that, oh, this is, I don't know if there is a metric of accuracy, but I think that the simulator was fairly good for the purposes that we wanted it to be.
Okay.
Can I ask a question?
Yes, please.
So you mentioned the historical data, just to be sure. So are you turning that historical data into some kind of forecast? I believe it's called hindcast forecast, the technical term for forecast that try to replicate what the situation would have been using actual data of the events that transpired.
Yeah, I mean, yeah. So basically, we were not even trying to do that, right? Like we're literally using the data at each time step. Like if we know the winds,
right? But you wouldn't be able to do that in a real-time situation, would you? So if you were to deploy this to
no. So that's the whole thing, right? Like I'm going to talk about this now. The solution is using the measurements, the current measurements, and then we also use some forecasts of the data, but of the winds. But the forecasts are often wrong. So the way we do this is that the solution is just using the current observations. It's not necessarily thinking about the past. But the simulator was just a way that we could try to iterate over this in a faster way, because we could do this in simulation, pretending we are back in time instead of actually having to fly the balloon all the time, right? Okay. So let me go to the solution. Maybe this is going to be clear. So how do we solve this problem? As I was telling you, like we don't even know how to properly forecast the winds. And we don't necessarily think that we had a really good solution for this. Like it was a really good solution, but like it's not the best possible thing that we could do. So but then if we want to think about AI and the existing techniques, like let's say the supervised learning, which is the most common one, this doesn't really fit the paradigm because we don't have a clean data set that we actually trust and that has labels of like this was the correct action to do. And in the same time, this seems to be the perfect place for us to use something that is called reinforcement learning. Reinforcement learning is this area of machine learning that one of the founding fathers, if you will, is Rich Sutton, who is actually at Amii. The book that he recently wrote, the second edition, is at the bottom here because I stole this picture from his book. But the idea is that the idea of reinforcement learning is to say, like, look, instead of expecting this labeled data set and then we learn patterns out of this, what if instead we think about AI just like as we or animals operate in the world, which is we interact with the world, and then we're going to observe what we're observing, and then we're going to act based on that observations, and then we're going to be constantly doing this. So that's what this diagram is showing. Like you're going to have an agent interacting with the environment, taking at each unit of time, the agent is going to observe a state that we call a state, and then the agent is going to take actions. And the goal of the agent is to maximize a special signal that is called a reward. So basically, you want to learn by interacting with the world to do the things that make you feel good and to avoid the things that don't make you feel good. And this seems to be a very nice paradigm for this type of problem. Like it's a perfect fit, and that's what we actually used. So to be more specific about this, the way we modeled the problem was that we had, at each unit of time, the balloon was receiving as input, like this AI was receiving as input as a controller, the state of the winds of the wind column where the balloon was. So like all possible altitudes the balloon could go to. What are the winds in those altitudes? Notice that we don't necessarily know for sure what it is. So we actually had three different information. We had the magnitude and the direction of that wind, but we also had a notion of uncertainty. How confident are we about those winds? Because the winds around where you are, they are you're pretty confident about them, but the wind's very far from you. Maybe you got a measurement a couple of hours or even days ago, so you're going to have a high uncertainty. And this is something that we were considering. That was the input to the balloon. Not only that, we also had notion things like we would call here, we are calling ambient variables, which are like, I don't know, what is the status of your battery? What's the time of day? And things like that. So that's how the balloon would perceive the world. The actions that the balloon was allowed to take were basically to go up, to stay where it is, or to go down. Meaning how this is actually converted in the real world is either you open the valve to let the air escape, or you pump air into the balloon, and then you know that it's going to try to go up or down, right? And finally, the reward function, or the objective that the balloon is trying to maximize, is this notion that if you are within this 50-kilometer region here, you're going to get a reward of +1. If you're outside, you're going to get a much lower reward, but this lower reward is going to decay with the distance you are from this region. So if you are closer to the 50-kilometer region, you're still going to get a small reward. It's kind of a gradient towards the place you are supposed to go, but you see that there's a step function here, so that here it's definitely better for you to be within that region. There was also a small penalty for using power. So we would always tell the balloon, like, you have to trade, like, this is a way that we can encode this trade-off. Like, yes, it's good to be within the region, but you also have to realize that you're spending power, and this kind of every time you get, let's say, a little bit hungrier or something like that. We used off-the-shelf solutions for reinforcement learning. And I think that this is important to say, because it starts just what this suggests, that we do have mature technology that we could use to make this work. Like, given the proper modeling, as I presented it to you, what we used was something that is called distributional reinforcement learning with distributed training. And I don't have to go into the details here. We actually had trained it for 30 days to get the final controller that we exploited. We use something that I'm particularly happy with, because it's something that I did during my PhD, which is this notion of purposeful exploration. But maybe the main thing to mention is that then we also used neuron, and this was all using a neural network as part of the architecture. And what this plot is showing here, I'm not going to mention the details of this plot, but what this plot is showing here is that we did do a bunch of studies of like, how big this network needs to be. Do we really need a neural network? And we needed a 7-layer neural network to get the best performance that we could. And that's what we actually did. So now I'm going to start talking about results. Do people have more questions?
Yes. I'm curious, why did you use DQN and not something more state-of-art, for example, soft actor critic? Because I think it would be more sample efficient, maybe.
So we used QRDQN, right? Like, which is a distributional RL algorithm. So it is fairly state-of-the-art, but it's a value-based method instead of a policy gradient method. I don't necessarily think it's that obvious that SAC is better than all the other approaches. It is definitely a good algorithm. And then at the end of the day, I think that so we had a couple of options. Do we use policy gradient methods? We did try some actor-critic methods, not SAC. Or do we use a value-based method? And at the end of the day, it was related to one, the thing that we were most comfortable with, and two, the thing that gave us an early signal that we could actually make progress on it. But by no means I want to say that if someone used SAC, it wouldn't have worked, or if it would actually have worked better. I don't know. This is the difference maybe between writing a paper, as we do, and deploying this in the real world, right? Like, it's not that easy to do all these empirical comparisons and all this analysis and this pairwise comparison to choose something. Sometimes you just have to get an early signal and ride with it.
Okay, so DQN worked pretty well for you, but you didn't compare it with like other methods yet.
Well, no, like we tried to do actor critic and we couldn't get it to work as well as we could with QR DQN, right? Like, I just want to stress that it's QR DQN, it's not DQN.
Okay, I see. Thank you.
Any other questions? No? Cool. So let me tell you about now the results, right? The first thing that we did then was to train these models. We used that notion of having an agent interact with the environment and so on. With that implementation, we did this in simulation. And then I can actually show you some of this data, and I'm going to play this video. That is while it plays, I'm going to explain to you what you're looking at. This is what was actually in production for Loon, what they actually had deployed in the whole world before we came in with the reinforcement solution. This is called Station Seeker, and this is a one valid trajectory. What you're seeing here is that we're showing the trajectory the balloon is going. The balloon wants to be within this region here, and this is just a top-down view of the same problem, right? The way Station Seeker works, it's a solution that is designed with control engineering principles in mind. A control engineer is the one who designed it. And the idea is that you want to have, like, given that you're observing the direction of the wind, you want to make sure that you have an acute angle between the wind and the goal and the place that you want to be. Because if you ensure that you always have an acute angle between where the direction the wind is blowing and where you want to go, you are always going to the direction of the goal. Excuse me. You're always going to the direction of the station. We call this algorithm Station Seeker because it's always trying to get to the station. And once it's go to the station, it goes back. What a horrible time to start sneezing. Once it starts to go to the station, it wants to go back and keep circling around, trying to go to the station. It has some other things like, sometimes it wants to explore to see what the winds look like, and it has a preference for slow winds close by the station and faster winds when it's away from the station. But this is the general gist of this solution. And this is actually a hard problem. Like I've been telling you that this is a hard problem, but maybe you don't believe me. So what I'm going to show you here now is 16 different trajectories of what a random walk looks like. So basically, if we had a balloon just acting randomly, this is what it looks like. So you see that, like, the balloon immediately veers off the region, and it's really hard to come back. So it's a fairly difficult problem that if you just act randomly, you're not going to do much progress. And hopefully you can see the contrast between that solution and this solution. So, and just to show you again, like here, this is the overlaying now the random walk that it's in light red, and actually the Station Seeker solution that we're showing blue. Sometimes it's important to mention this. There's nothing you can do. Sometimes you don't have winds in your favor, and you just have, and basically you cannot be in the region. But several other times there is a lot you can do, and I think that this is a distinction that you can have, right? So now finally, I want to show you what the RL agent does. And this is a little bit more of a convoluted plot. So at the bottom here, this is what we're going to show you here is the trajectory of first the random walk, first the Station Seeker, sorry, and then the RL controller. Here, what you're going to see over here is time. It's training time, so it goes from 0 to 24 days of training. And in the y-axis, we have the percentage of time that we stay within this radius of 50 kilometers. Okay, so and this dashed lines here that we're going to show is that this is the performance of the Station Seeker, and the yellow one is a performance of a search-based controller. So if you're familiar with planning, this is doing tree search. It's not realistic because it doesn't work in practice because it needs to rely on having a very accurate model of the winds, and as we have established, we don't have that. But we do know what the winds look like in simulation, so we'll use that in a sense as almost as an upper bound, like how well could we do? right? Now let me play here so you can see how we train over time and how the performance improves. So this is the station seeker, just to plot again. This is what the RL agent looks like at the first hour. So basically it starts randomly, so there's nothing much you can do. But then as we keep progressing, you see that it gets better and better. So after 6 hours, it was already as good as the solution that was being in production. And then we kept running longer. And after 4 days, pretty much, we got the agent that was as good as this, what we consider to be the solution that if we had access to the winds. And then it just kept going, and it kept getting better and better until getting to 24, the performance that I showed you. This is just a different way of showing the same results. I just like this plot because it highlights the multi-objective aspect of the problem. Because what we're showing here is that this is, again, the time within radius of 50 kilometers. So that's the metric that I've been showing all the time. But now in the x-axis, what we're showing is power. So arguably, you want to be at the top right corner here because you're using very little power and you have a very high accuracy. But of course, we don't know how to do this. And what we're showing here is that are all the possible trade-offs that we can get with this agent. So all these regions here that are in blue, this is what we would get with the different changing parameters of this control engineered solution. If we do the same for the search controller, you see the same thing here in yellow, showing that there's this natural thing that maybe you can get a little bit more accuracy, but then you need more power and so on. And then this red curve here is the controller that we had over different times of training. And what you can see is that we start after 12 hours, we're fairly good, but then we just keep getting better in terms of accuracy. But it's not only that we get better in terms of accuracy. Over this training for this, we also learned to go right here, meaning that we ended up being energy more power efficient, right? And what we wanted, one of our goals in simulation was to make sure that we had a controller that was using as much power as the controller that was in production. So this is why we chose this one. It's like, okay, it's using the same amount of power, but it's much more accurate. There are different ways of showing this data. This is just the same numbers that we had before, like it's 55.1 is what we actually get with the learned controller, while the station seeker, the baseline was 40.5 in simulation. There is this question that we kept being asked, is like, how well can you actually do? Like, what is the best you can do? And as I was saying, like 100% is not possible because sometimes the winds are just not in your favor. So I'm not going to go into the details of how we did this, but we actually computed what we thought would be the best we could do. And we think that the best possible thing that we could do would be something around 60%. So we are very close to getting there. And I just want to remember again that this is a real world problem. So these numbers have meaning, right? Like each percent that we increase in terms of accuracy here, it generally means 50 more minutes of internet being served. So this is a big deal. 50 minutes of internet a day. This is the most complicated plot in the talk, and I'm going to just gloss over it. But I think it's also important to talk about this in terms of the big picture of deploying machine learning models in the world, which is people are often hesitant of just saying that, okay, I just trained this black box and I'm going to deploy it in my product, right? So one of the exercises that we did was to try to actually understand what was that this agent was doing. What you see in blue here is that this is what station seeker does, and maybe the plot on the right is easiest to understand, which is to say that if you are close, what this is showing is that if you are close to the station, like from 0 to 50 kilometers, magnitude here is the wind speed. You want slow winds, but as you move away and away, you probably want faster winds, right? And then you see that this is a fairly smooth curve. The same thing is for the angle. And one thing that we can see here is that we don't have the same nice shaped curve when we're talking about the learned controller. And this is, in a sense, maybe it's expected. This nice smooth curve is because someone actually wrote code and designed a solution based on control engineering principles. So there's only that much you can think in terms of nonlinearities. While this is what it was learned. So you see that it's a fairly non-linear solution that gives different priorities about the magnitude of the wind or the angle and so on. And I think that that's something that it's also important to think about how we can try to better understand the solutions we come up with if we're going to deploy them, right? And then we go to the deployment phase. Are there questions for the simulation?
Just a quick question. So after 6 hours, it achieves very good performance. Is there a need to do a better job in the first 5 hours, or is it okay to do not well?
Well, we're doing this in a computer cluster, right? Like, it's not that we're deploying the balloon and we're waiting 6 hours for the balloon to actually do well. We're training this, and once we have a good model, then we put that model in the balloon and we say, go fly. So, of course, we would like to get results as fast as possible to be able to iterate quickly, but there's no cost in terms of actual performance on those first 6 hours, right? Like, we're just waiting for it to learn the solution that we're then going to actually use.
Oh, okay, thanks. Yeah, I guess I will need to wait for deployment phase to understand.
Yeah, so what we did then was that we trained these agents as I showed the performance, and then we had a trial run. It was very exciting. I think it was June of 2019, where we had a meeting when one of the Loon engineers showed us this plot, and then we're like, oh, cool, we are used to seeing these plots now. And I was like, no, you don't understand. This is your algorithm. And I'm like, what? Is it actually running in the real world? And he's like, yes, we wanted to see how well it was doing. And we saw a lot of things that we're happy with in this plot. And basically what they did was that they literally, in a sense, copied the brain, and then they put the brain inside the balloon. And what we saw, a couple of things that we were happy with, was the stacking behavior, for example. This is fairly common in sailing, and we were used to seeing this in the other solutions of the balloons as well. What this is showing us is that there is no direct wind that takes you from here to here. So what you do is that you kind of navigate around, and then here you say, oh, now I'm going to change altitude because I can go this way, and then you present the stacking behavior. So we saw that, oh wait, our solution did actually learn. While in simulation, when we deploy it in the real world, it did learn to go towards the target. And once it was within the target, we could see that it was going around and staying within the region. So we were like reassured, it's like, okay, what we're doing is meaningful. But then, of course, after we do this, then we have to be more serious about evaluation and not just deploy any model. And I don't know if it's clear to you at this point, but like our agents always had name of pastas, so that's why we have here cannelloni, for example. But then what we noticed is that if we were to look at this agent that we just deployed, which was cannelloni 7 at the time, it was not necessarily that better. Like, it was using the same amount of, it was a little bit better than Station Seeker, but it was not even the best agent that we had trained and then we were evaluating. So then we said, okay, we can be much more careful about this. So we took a couple of months to be careful about evaluation, to understand these things and actually squeeze every bit of performance that we could. And then in October, from October of 2019 to January of 2020, so it was a 3-month period where we actually got 13 balloons and we deployed them in the Pacific Ocean. And we let them run there for 3 months. 7 of these balloons were running the baseline, the Station Seeker, which is the solution that was the control solution. Another 6 of these balloons were what we were now called Perchatelli. They were using our solution, right? We had, at the end of the day, we had almost 3,000 hours of flight hours of reinforcement learning for this experiment. And the goal is, as the title says, that we were trying to do A/B testing the stratosphere. We wanted to see which balloon was better. Then, of course, it's a very hard problem to ask because it depends. Like, I cannot just deploy a balloon in Peru and one in Kenya and say, oh, which one is better, because it depends on the winds and so on. So we tried to put them in the same region. Of course, we could not put them exactly at the same location. But then we let it run for 3 months to get enough data to be able to actually make claims that are statistically plausible. The numbers at the bottom here have the final performance that we report. So the time within radius of 50% of 50 kilometers of our agent was 79%, while the time within radius of the baseline was 72%. You might be wondering, like, wait, these numbers are much higher than the ones you were showing until now. Yes, because in the simulation, we were actually exposing the balloon to very difficult conditions. So the balloon would learn the best it could for all sorts of variations. But then it just happened that in the 3 months that we let the balloons fly in the stratosphere, the winds were more friendly. So we managed to get this 7% gain. And again, if you think about this from a notion of each percent is 50 minutes, it means that we've got almost 2 extra hours of internet a day if we were to deploy this RL solution. And we're also more power efficient. We were using 29 watts on average instead of 33 from the station CIFAR agent. So that was a big win. We now had data from the real world showing that our solution was actually good. Then we start to ask, like, what is it doing differently? Can we notice a difference in behavior? And we could. So if you look at here, the blue curve, for example, you see that there is a lot of curves overlapping this center region here, which is this notion of it's constantly trying to go to the station, for example. While here, what this is showing is a different profile. What our agent learned to do was that I don't care so much about the center. As long as I'm within the region, I'm happy. And in fact, it was really happy to be within this from 25 to 50 kilometer radius, maybe because it had a bigger space for maneuver, like, okay, and then it could just coast. So that was fairly interesting because it's a behavior that just arose. We never coded that up. They learned to do this, right? And we have data to show this. Like this is showing exactly like how often it stays within each distance. So you can see that it likes to stay like this is the big gap, but like let's say that this is 25 kilometers. So the red curve is a big mass of it is here, while the blue curve is really worried about getting as close as possible from the station. And it's not only that. The other thing that we notice is that at the moment that the balloon went outside the 50 kilometer region, the learned controller was much faster at coming back to the region than it was the other solution. And you can see this, like the excursion is like when you go outside, and it doesn't matter how long it is, you always have like a bigger mass, or like you have a shorter excursion for the red curve, meaning that the learned controller was better. I think that what's interesting here is the notion of power, because I think that it starts to explain a lot of this behavior. So in this region of from 0 to 25 kilometers, we couldn't make any distinction. They were acting similarly in terms of power profile. But when we look at this region from 25 to 50 kilometers, there is a big difference. And the big difference here is that our agent, our controller, is happy to be there. In a sense, it can just coast like, well, if I'm not being blown away and I have to make sure that I correct for that, I'm okay, I can just wait. While the station CIFAR agent has this need to always be looking for the station. So it was always trying to do this. So we were more power efficient here. Meaning that then we had more power saved when it was needed if we went outside the range, because then we were going to use much more power because we had that power available to make sure that we would go back sooner, right? So far, what I have showed you is that, well, we do get a more precise controller that is more power efficient, and so on in a multi-objective way. But there is also more. Like another thing that we did was to look at the robustness. So this is a simulation, but we put a bunch of balloons to fly side by side. And the idea is that, well, if they are very close to each other, we would hope that they would clump together, meaning that small variations in the initial condition shouldn't matter so much in the performance. And what we noticed that our learned controller, which is in red, again, is more robust than the solution that was being deployed until that moment. So what you're seeing here is that is the distance to the station. So lower is better, and red is often better. But then what you're seeing here on the right is the distance between the balloons. So like basically, if they're very clumped together, you would have 0. And what you see is that pretty quickly this solution, this control engineer solution, it starts to scatter around, meaning that even the small variations that they started with lead to very different behavior, because this is a chaotic system. But in a way, we learn to do much better than that. Okay. And this is the last result that I want to show you, which is maybe the one that I'm most excited about, which is this notion of, as I was saying, we're solar panel, like we're solar powered, right? And then we were looking at one thing that we noticed is that we were looking at the average altitude over time. And one thing that we noticed is that our learned controller was consistently being at a lower altitude during the day, at a much higher altitude during the night. And then we were like, why is that? And then we asked the Loon engineers, and they come up with this fascinating hypothesis, which is the following. To go up, all you have to do is to open a valve. Air is going to go out, and then you just go up without taking any extra power. So what our balloons learned to do, what the solution learned to do by just interacting with the world, was that if I go to the bottom, like to a lower altitude, I get to store potential energy. So in a sense, I get to have more power. So now, overnight, because I learned to store potential energy, I can just open the valve if there is a bad wind where I am, and I just get to explore all that range in a way that basically I wouldn't otherwise be able to if I didn't have power. And you have to be very power conscious about it, mainly at night, because then you have to wait until the sunrise to get power again. So if you run out of power, a bad wind can just blow you away hundreds of kilometers from where you want to be. And I thought it was fascinating to see like something that we never thought about, which is storing potential energy as part of the solution, because it's very hard even to code this app, right? Trading off all those things, it just naturally came out of the solution. So just, and again, this is in the real world. This was actually deployed and provided the internet in Kenya. So it's not that we're just doing this simulation and in controlled environments. No, this was deployed and was providing internet to people in Kenya. And it's a solution that it's not only a solution that, oh, I execute this for a couple of minutes or hours and then I'm done. Like these balloons would be almost a year in the stratosphere. So you needed something that was robust enough that would actually be there and have an effect for extended period of time, right? This is not something that reinforcement learning is frequently doing, this type of solution. So just to wrap up, and then I'll take questions. I want to, maybe the final message for this talk is that reinforcement learning works. Of course, it's quoted here because I think that it works in a class of problems within safety layers with large amount of training, but it works. We are getting to a point that we have a mature enough technology that we can actually deploy this and be able to do things that otherwise we wouldn't in the real world. There's this meme that reinforcement learning doesn't work, and I think that we start to challenge this. This happened in 2020. This year, there was a result about people using reinforcement learning to actually control nuclear fusion. So I think that we're getting to the point that this is a viable technology for us to deal with problems. I think that there are a lot of lessons learned about the importance of feature engineering, of sim to real, generalization, how to deal with exploration, getting the detail. But let me just say that getting the details of deep reinforcement learning algorithms right is quite important. But I'll stop here and I'll let people ask questions to make sure that we have some time for that. Thank you very much.
Just one question. So how did you do sim to real? Did you just use your trained agent and just change the environment to the real one?
Yes, I mean, when we were doing the simulation, right, like we had this problem of like having the coarse winds. So we had to add noise like we had to interpolate, and we did this by adding noise, and we had a lot of, basically we added noise and this uncertainty. There's a scientific question about the role of uncertainty here, but by having the uncertainty, by adding noise in the simulation, so on, this allowed us to deploy this in the real world and get it to work.
Oh, wow. Did it adapt in when being deployed in real world? Did it continue learning? No?
No, it was a fixed solution. We didn't
learn. Wow. So, but it still could do well throughout the year, even though the solar irradiation changed and wind patterns changed and temperature changed.
So just to be clear, it was not flying for like that plot that I showed that it was a whole year. The balloon was not flying there the whole time. But yeah, like, well, at least for, trying to be conservative and not make claims that I cannot support with data. At least for those 3 months that we were doing the real world evaluation in the Pacific Ocean, right? Like that was running for sure. Reinforcement learning, it just worked. So, and then we deployed it in Kenya and it was working well again. So.
Oh, wow. That's still very impressive.
Thank you.
Mika, probably next question from Mika.
Hi.
Oh.
In reinforcement learning random, or is there a way to predict what solutions the model will come up with?
I'm not sure I understood your question. Can you say a little bit more?
Sorry, I'm just outside. Just curious, new to the whole reinforcement learning idea, and I'm just wondering if the solutions that reinforcement models come up with are they random solutions given the data being given clear information? Do the models come up with random solutions that fit in ways that we could not perceive? Or is there a way to determine what solutions would work?
Well, it's so I'm hesitant of using the expression random solution. I think that what's going to happen is that these agents will find a way of maximizing reward that could be not what you're looking for, right? Like not what you would be expecting. And in a sense, that's the beauty of it. Like it's a feature, not a bug, because if you specify the goal and you say now figure out how to specify that, how to achieve that goal. If you knew how to do it, then you might just as well code up the solution. Can you guarantee that it's always going to be exactly the same solution? No, there is a lot of stochasticity in this process, right? Like if we want to be a little bit more technical, it's a non-convex optimization problem, meaning that even different initializations of your neural network are going to lead to different solutions. But what we notice is that this is fairly robust, right? Like we could consistently get this over and over again. GM, I guess.
Yes. Hi. Yeah, that was a really great talk. Thanks for that. I had two questions, but maybe I'll start with the one that I most pressing to hear an answer for. So the way the reward signal has been encoded, as I can understand it, is in terms of the balloon itself being within some proximity of some specific location. And I was wondering if there was any way to more directly encode the reward signal such that it talks more towards the actual thing that you're trying to do here in terms of that is provide internet. So is there some way to formulate the reward signal such that it directly relates to maybe say the strength of the internet signal or the speed or bandwidth or what have you? Perhaps another way of asking the same question is the signal more or less the same within that 50-kilometer radius, or does it deteriorate significantly enough that maybe if your model, which seems to stay somewhat further out than the signal seeker, I forget what it was called, the station seeker, yes. So it looked like it went a little further than what the station seeker did on average, and that in doing so, it somehow ended up giving a little bit more in terms of signal uptime. But would the signal strength, follow be as good, or would it deteriorate enough to maybe cancel out or negate that extra time?
So my initial reaction is that within that radius, the signal should be good enough that this shouldn't matter. I'm not an expert on that communication aspect of the problem, right? So in a sense, this was the goal that was explained to us by the Loon engineers. Like within this region, if you're within this 50 kilometers, we're happy. We're very happy. This is the goal. So this is what we set up to do. And I think that the reason for this is because within that region, we're fine. Yeah, because like from an RL perspective, right? Like we learned a lot about their problem, but I couldn't understand. I didn't learn about the whole pipeline. But the fact that they deployed this in Kenya, they have very little incentive to deploy a suboptimal agent, right? From a Loon perspective, they're a company that are trying to provide internet to people, good internet. And that's what they did. So it seems that all the evidence that I have and from the conversations that I have, if we are within that 50-kilometer radius, we're good to go.
Okay, that makes sense. Thanks.
Thank you.
We are actually at 1 o'clock now, so it's kind of the end time for us. We don't have any room to take any more questions. Probably if you have any more questions, you can send an email to us. We can send those emails to Marlos, and he can reply to your questions. In any way, thank you again so much for joining us for this month's AI Meetup. Don't forget to check out our next meetup on July 19th. And have a great day, everyone. And again, thanks for joining.
Thanks, everyone. Have a good day.
Thanks, Marlos. Thanks.
Thank you.